Okay, so welcome. This is, as it says, CET466. It's called Logic Design. I am suffering, and I told a lot of you yesterday that I'm suffering from an abrupt change from online teaching to in-person teaching. So I've tried to set up something here that allows me to record everything, so that if you miss a class, there should be partial attempt to record it up on YouTube available to you. Okay, so that's what this is doing. This little, it's actually a PS3, PSI, is this called? Is not actually working as a camera. It's just because the microphone on this old machine is dead, and I needed some way of getting voice on it. So that's what's happening. My name is Peter Koutsoukas. Feel free to call me Peter. Professor works, Hey You works, whatever you feel like. I saw this meme and I thought it was quite relevant to what we're going to be doing in this class, right? So some of you may have programmed in Python, some of you may have used C or C++, some of you may have touched assembly. Anybody played with assembly code? No? Okay. So anybody touched C or C++? Some of you touched C. No? How about Python? You got 1, 2? Okay. So the thing is, the thing that right, so that it's a bit, might be a bit hard to read, but the first one here is saying, wait, it's all abstraction, and they're the Python programmers. And then everybody behind them is saying, always has been. Right? Because the stuff we're doing on the computers is built all the way down to transistors, and if you want to get really funky, you can go down to a more elementary part of it, right? And the thing I don't like about this particular meme is the stuff we're going to be doing is sort of fitting in here and sort of fitting in here, right? Because you've all done, what's it called? Digital circuit, CET466. And what we're doing here is we're now taking that information about logic circuits, and we're doing, and you probably used 7-4 series integrated circuits to build some circuits. Those don't tend to be used as much these days. Logic is still important, but they tend to do it in different sorts of devices. And in particular, let me just unpack that. And before I'll pass it around in the anti-static bag, probably that helpful, but anyway, hopefully it'll stop it. So the big square chip on the left middle here is an FPGA. That's called an FPGA is Field Programmable Gate Array. That's the things we're going to be using in this class to convert a logic design into something that actually works. Okay, so that's that. So, good morning. So like I said, my name is Peter Koutsoukas. Happy to have You just call me Peter, that's good. So I wrote a little app because I always have trouble with student names, and I still have trouble with student names. And with the masks on, it makes it even harder for me. So I have this. One of the nice things about running online, and you've heard the capstone students have heard this before, one of the nice things about running online is I could run classes through Discord, and I had a nice little Discord bot that I could, one of the things it could do, Professor Broderick started it and then I helped him update it. One of the things it could do is randomly choose a student and keep track of who it had called to ensure that everybody got called at some point before it reset. And that's what this app, that's the main reason I wrote this app. So that's me. I have degrees in electrical engineering and systems engineering. I did a graduate certificate in, system design and management at MIT when I was working at United Technologies, as it was called then. They were kind enough to pay for me to do that grad cert, which was fun. That's my email address. I believe most of you are computer engineering technology students, and we have one or two cyber security students. Yeah. So that's good. So what I'm going to do now, I'm going to put you all individually on the spot, and I want you to, I'll call you randomly. I want you to tell me your name, just so that I can make sure I can get the masked face lined up with the name. And I want you to tell me something, anything that you learnt in 363, if you can remember back though somehow. Okay? So let me, so the app puts the students here, and I can go down and randomly choosing Emily first. So
my name is Emily Bodak, and I guess I remember like the 4-bit parallel adder like laughs.
Okay, 4-bit parallel adder, that sounds good. Okay, so next up on the list is Anas. Yeah.
I'm Anas Salomon. I'm a cybersecurity student. And something I learned with 363. The D-latch and the other ones. And
okay, D-latch.
And just doing the physical labs on the Blackboard, just connecting.
Yep. Okay. So next is Muhammad.
My name is Mohammed Khan. Something that I remember from 363 was I think the digital timer project that we had. I just really like that one. That's it.
Okay, sounds good. Matthew. Yeah, Matthew, there you are. Yeah.
Hi guys, my name's Matt. Something I remember from 363. Yeah, I guess the adder.
The adder? Yeah. We're going to get very familiar with adders very shortly, so that's okay. And Charles is not here? No. Okay. I might have to, Michael.
So my name is Michael Frederick. I really don't remember taking 363, or here at least, but I do remember like logic gates and stuff.
Okay. Sounds good. Eric.
My name is Eric Berson, and from 363 I remember flip-flops.
Yeah. flip-flops. We're going to try and think about flip-flops. In fact, I think we may actually implement a flip-flop or two. So, and I might. Where's Dave?
Yeah.
There you go. Hey.
Yeah, so I'm David Young. I remember Boolean algebra.
Oh, yeah, good. Boolean algebra is good. No heaven, I don't think, no. Let's just see who's left. Okay, so. Michael?
I remember Broca in 363. I remember different logic gates or gates and average speed.
And yes, that's very good. Right.
My name is Mike, computer engineering major. I remember from 363 was Boolean expressions and logic.
Okay. So, it looks to me like Mike is the last one. So, who's here anyway?
I'm Mike. I work in the calculator lab. We did manipulating calculator circuits.
Okay. Okay, that's good. So, let's. So this class is aiming to take that information that you know from logic and teach you a programming language, which is VHDL, right? So that we can, where's that board? I'll go and grab that board. So we can program in VHDL to do hardware things. And the one, if there's one key piece I want you to take away about VHDL as a programming language, is that normally with programming languages, things happen in step, in sequence, right? The nice thing about VHDL, and it's going straight on the hardware, is that unless you encapsulate the instructions, everything happens at the same time. Right? There's no sequence. Everything is connected the way you tell it to. You can make it sequential because that's useful. But in general, everything's happening at the same time. And that makes life a little bit more interesting.
Professor,
Yeah.
what does the acronym stand for?
This one? Or
Yeah,
VHDL? FPGA is Field Programmable Gate Arrays. Okay. There's a few other sorts of devices that we'll talk about in a bit that are a step up from the 7.4 series devices that you've used in logic design, in digital circuits. There's PLAs, which is programmable logic array, and there's another one, and I have forgotten the other one. We're focusing on FPGAs, which are a little bit more functional than PLAs or PALs. So one thing I try to do when I teach courses is I try not to teach them the same way every time. The reason I do that is because if I tried to teach them exactly the same way every time, I would get bored, and you wouldn't like me when I'm bored, right? So I try and make things interesting for me as well as interesting for you. So previously I have not had a textbook for this course. I have decided this time round that I'm going to have a required textbook. It's an online textbook, and it has lots of, I think, quite good examples and case studies that I think will help learning this course. So please get access to the textbook. I noticed several of you have already done that. What I'm aiming to do is, within the textbook there are two sorts of, if you like, assessment things. There's a what do you call it? A participation activity, which is basically one way to think about it is, in a normal paper textbook you've got examples, right? In this one, the participation activities are basically animated or interactive examples, so that you can move things around and you can get everything right. It just, you've got to choose the right thing. You don't have to go with one example or one selection. You can change your selection to get the right answer. So I set that first participation activity to be due at 8:30 this morning. However, I know we hadn't had a class yet, right? So if you have done that participation activity, thank you very much. I will open it up for everybody else again, but the people who have already done it, I'm going to give a bonus grade too. Okay, so if you've already done it, that'll be my usual bonus is about 5%. So please get access to that. If you have any trouble, just let me know and I'll try and deal with it. You will have to sign up with your CCSU, my.ccsu.edu email address. There we go. So during class, I want you to review if I give you something to read or participation activity, please do that before class. I'll try and set everything up on the Saturday afternoon after the class, so that you've got access to it for the week. This class is going to be heavily lab based, right? So you're going to be using MultiSim and an IDE that Altera puts together called Quartus. Quartus compiles VHDL and talks to these boards. In addition to the participation activities in the textbook, there's also these things called challenge activities. They're a bit more difficult, and they're also part of the assessment, which I should talk about shortly. So that's our semester. This column is basically just a list of topics. It's really not, I'm not going to be covering them in that order. The main interesting thing will be the lab list and the dates. I think last time I taught 363, this was the textbook I used for 363. So I'm going to be using some slides out of that, but you don't need that textbook. I can provide all the material you need for that. Okay, so that's the, this might be a bit small to read, I should have made it a bit bigger. That's the assessment, 10% on those participation activities, and it should be very easy for you to get that full 10%. The challenge activities, like I said, are a little harder, but that should be 15%. The labs are worth 25% all up. I think I've set up 8 labs already. I'll show you in Blackboard shortly. At the end, for the last month of this course, I think if you have a look at the schedule, maybe it's a bit longer than a month, I'm going to get you to pair up and do a group project. One of the nice things about these boards is it's got lots of I/O. It's got some 7-segment displays, it's got some LEDs. Where are the LEDs? They're over there at the top there. It's got a buzzer, and it's also got a VGA out. Right, so you can make video. This board create video, which is kind of cool. One of the groups I taught a while ago now, I've forgotten when they actually made a little Pong game that displayed on the video, which is kind of cool. Okay, what else we got here? So one of the things that I changed when COVID hit back in March last year is I changed my method of assessment for exams. Now I do exams on Discord or whatever, but they're oral exams, right? So treat it like an interview. People think I'm crazy when I tell them I release the exam at least a week, but usually 2 weeks before you have to do it. So you can see exactly what I'm going to ask you, and then it's up to you to be able to answer it. Now, one of the catches is sometimes I will have a question like, here are 20 topics that we've covered in this course. I want you to choose 2 and tell me about 2 of them, and then I'll choose 2 and you need to tell me about 2 of them. But I'm not going to tell you which of the 4 topics. You can choose 2, so that's easy. But I'm not going to tell you which of the 2 topics I'm going to pick. So you're still going to cover it, and it's just I'm only going to touch in depth on particular ones. But I'll go through that when we get closer to the time. One of the things I did last year, and I decided, well, this is another change I've made from last year. I decided last year that to incorporate this MHRD game, which is basically programming a simplified version of VHDL to build a CPU, right? And it starts off with you've got to build an adder, a full adder, and then you've got to build a 4-bit adder, and then you've got to build various other components of the CPU, and then you've got to put it all together. And it is quite a good representation. It's not exactly what we have to do when we build in VHDL here, but it's not a bad representation. You'll notice the numbers here should add up to 110%. This is completely optional, right? If you want to do it and you complete the game, that'll be worth 10%. You don't have to do it. Some people are more. It's available on Steam, I think. So have a look at that. So the project should be a largish project. Do it with a partner. It should solve a reasonably complex digital logic problem. It has VHDL tests associated with it. There are no glitches or hazards. It runs on the boards we have. It's performed with one partner. So one of the things I hope you get out of this course is the idea that any design, producing a product, is a process, right? My kids, when they were in elementary school, right, it was plan, do, review, right? And that's basically the same sort of stuff, but now we're on the engineering side and we're doing stuff. So we design it, we implement it, and we verify. Right? So the design is the paper design usually. Maybe it's in MultiSim. The implement for this course is writing code in VHDL for the most part. And then the verify is, nice thing about Quartus is you can simulate what's happening in the VHDL code and exercise that code with test cases and check to see whether the code does the right test cases. So that's something that we'll get there before you have to do the project, but that's one thing I want you to do. So, and again, this is probably a little hard to read, but this is one of the questions from last year on one of the exams, right? So that's what VHDL looks like. It may look a little like gobbledygook at the moment. If you've programmed in Python, the top things there, the library and the use, they're like Python import statements, right? And then what we're interested in with VHDL is inputs and outputs. When you see the keyword entity, that is saying, here's something that has inputs and or outputs. Right? So this entity is called question 1, and its definition ends down here. And you should be able to see there's lots of inputs and there's an output. Okay? All that just defines how the device looks to the outside world. The thing that tells you how it works is the architecture. And that's an example of an architecture. I said earlier that everything in VHDL is in parallel, but you can block it up to make it sequential. But one way to block things up is to use process statements. Okay? That's why if then else's work in VHDL because they're blocked up. Okay, so that's the code. Let's see what the question was asking. If I can figure out where it is. So the first question was, what does the listing do? Because it didn't actually say what the oops. Went all the way to the bottom. Okay, not too far. It didn't actually say what the listing did. One thing I'm going to want you to do in the VHDL code you write is use comments, so that at least your intention is clear from the comments, even if the code doesn't necessarily implement. So what this code does is it implements a dual port RAM. Anybody know what a dual ported RAM is? None of you are gamers? You're into graphics cards and stuff? So the thing with RAM, random access memory, okay, is you often want to write to it and you want to read from it. And the problem is, if you've only got one port, one access mechanism into that RAM, you can only do one of those things at once. If you have dual ported RAM, it means there's two ports, so you can write to it and read from it at the same time. Okay. So that's why dual ported RAM is important. The reason I mention video cards is because oftentimes with displaying the output of video cards, the actual display mechanism, the projector or the LCD display, needs to read the information to put it on the screen. But the compute engine is calculating all those triangles that graphics cards do and pushing it into the RAM. Right? So you need to be able to do both of those things at once if you want to do it efficiently. And then this particular question 2 here is just explain to me this generic keyword. And it's like the it's like just declaring a constant, a named constant in most other programming languages. Okay. So I have a few people to thank. Professor Zanella gave me a lot of the notes I have for this course. So that was very good. A former colleague of mine in Australia, Jasmine Banks, is now at QUT, Queensland University of Technology, and she gave me some of her notes for, again, a similar course that she teaches at QUT. Johan gave me some of his notes. He has some quite excellent notes about programming in VHDL. Professor Schonken is, I thought about using this book, but it's a little bit too focused on the software side. He has this book called NAND to Tetris, and it basically takes you from logic design, NAND gates, all the way up to writing a program to implement Tetris. And it's that last part is a little bit too far away from where we are here. So. And then last fall, the guy who wrote MicroHard, that MHRD bonus game, gave me some game keys so I could try it out. past quarter. I decided not to ask him for more this year, but I will point you in that direction if you want to do the bonus. Okay, I've been talking for a while. Does anybody have any questions so far? You all good? Okay. So I'm going to take a quick. Let's do that. I'm going to have to take a quick walk through the syllabus just to see if there's anything okay. Okay, that all looks good. Please get the textbook. I do not have an office on campus, so I can't have traditional office hours. I have a Discord server. If you want to contact me that way, that's okay. I have, if you, let me see if I can. If you go into if you go into Blackboard, I have a section in the class. I don't know why it's decided to show me the mobile site. Anyway. I have a section in the class called Tools for Remote Work. And there is a link here which is booking for exams and general consultations. If you click on that link, it will take you here. And at the moment, I don't have any free time. I haven't set that up yet. But what you'll see is you'll see all the dates where I have free time made available, and you can book time to talk to me then. And we'll talk via Discord or whatever remote mechanism you prefer. I tend to prefer Discord. Right, so that's the Discord server. If you join there, you won't. If you haven't joined yet, if you join there, you won't see the 466 Logic Design materials and discussion yet. I'll have to add you to the appropriate role on Discord. So one thing that's different about doing an online oral exam is it's not going to happen during the final is not going to happen during the scheduled end of semester time slot for this course. However, you can book a time that suits you, and I usually make more than enough slots available for people to book, and some of it will be during finals week, some of it will be before finals week, some of it will be after finals week. So I suggest you choose, once those slots are open, I suggest you book them as quickly as possible because they tend to go quickly. Or the favourite ones for particular times. Right, so please get things in on time. The initial participation activity closed this morning. When I get home this afternoon, I'll reopen it, so you have another week or so to try and get it done. I really don't care when you get stuff done, except I made the mistake of making everything available whenever the students wanted one semester. That semester, in finals week, I had to mark 1,000 things. I'm not going to do that again, right? So you need to keep up with the due dates. Having said that, I do know stuff happens, right? So I allow every student the possibility to submit 2 items of any particular type late for no reason. You don't have to give me a reason, just say I want to submit this late, and that means you can blow off the first participation activity, challenge activity, and lab, the first 2 of those 3, and then hand them in at any time. After that, there's no slack. You've got to hand in everything else. But save them up. Leave it until midterm time or the end of the semester. That tends to be the crunch time for everybody. So have a look at that. I'm hoping we can continue like this for the rest of the semester. If things shut down, I'm going to go into the mode that I used last fall. I will get every one of you one of these. Even last fall, I was able to get students access to this lab provided there were no more than 2 or 3 people in the lab at once. Right? That way, if you can't install Quartus on your own, you can use these machines to do it. I'm hoping that won't happen. Just as a contingency, think about how that might work. There's lots of VHDL code on the internet. Don't copy and paste it. I will find out. It's pretty easy. It's amazing how easy just copying somebody's code, pasting it into Google, and it will tell me exactly where the code came from if it's been copied. All right, so don't copy it. If you have any special needs, please let Disability Services know, and they'll let me know if I need to do anything to accommodate you. I'm happy to accommodate anybody for anything. As you'll notice, I wear hearing aids, so you may have to shout sometimes, particularly with these things. One thing I've found with these masks, and I will wear them, I'm perfectly happy to wear them, I didn't realise how much my hearing depends on lip reading, right? And I can't lip read anymore, at least not in this environment. So it can be a bit of a struggle for me. There's the schedule that should be the same as what's in the PowerPoint slides. Have a read through one of the, I meant to look it up, I forgot to look it up last night. I think he's either a philosophy or an English professor here at Central. He came up with a nice list of things to do about COVID. So if you're not fully vaccinated yet, please get fully vaccinated. Good to see everybody's wearing face masks. Try and maintain social distance. If you realise you're exposed, get tested. One thing I hope that happens a little bit more, even for just things like the flu, is that people are able to take time off study or work a little bit more to stop infecting other people. one of the things I haven't seen the figures for the US, but in Australia, the last year, flu season, was virtually non-existent. Because everybody was masked, because Australia was locking down harder than we have in the States. They usually have, I don't know, forgotten the numbers, they usually have maybe 10,000 significant flu cases per year in Australia. I think they had 5, right? It was just ludicrously low. And I think I already mentioned. I'll give you plenty of notice. If we go remote, it'll be on Discord. I've found that's a nice way to do things. But I'll only be using Discord for the midterm and the final, as plans stand now. Okay. So all of these notes are available in OneNote. So you should have access to that. Right, what you should be able to do is, even if you don't have OneNote installed, no, let's do that and actually use the HTTPS, maybe. There we go. So even if you don't have OneNote installed, you should be able to see everything in the oh, that's the wrong place. Those are the wrong place. Oh well, I should move those over. You should be able to see everything. There's the draft syllabus. My notes for today are up there. So that's the slide deck. I've put up the full 2020 midterm, so you can have a look at that. I'm going to do it a bit differently this time around. I've learnt a bit since I did this one, but might as well have a look. And there's the final. If you've ever wondered why, what the teaching evaluations that you do at the end of each course look like, that's the teaching evaluation from last fall. And I think the main feedback was everybody had to, last fall, everybody had to do the labs on their own. And that was a real stretch, right? Some people were okay with it, a lot of people weren't. The nice thing about being in person is it's in person, right? You can see what everybody else is doing. One of the things, I don't know, I have this theory that one way people learn is by osmosis. Just being in the same room as other people learning the same stuff. And I'm not sure exactly what the connectivity is, but it's not just me, it's having your peers learning at the same time that I think helps, which online tends to cut down on. Okay. If you haven't looked at it already, I suggest you check out the assessment calendar in Blackboard. If your professors use Blackboard and set due dates in Blackboard, all the dates are up there. Even better, If I can figure out where it got to. Down here, you can get an external calendar link and put it into the calendar app on your phone, and it will show you all the due dates. And it'll update them if they change. Right, so you can see this is the summer course, I think, that I had. And this is the capstone course. But here's the participation activity. And then there's a lab, and then there's going to be another the challenge, and then there's going to be a participation activity before next week's class. Okay. I think that is all the red tape. Any questions, comments, concerns? So I had somebody ask me yesterday whether I'd be talking for 4 hours this morning. The answer is no, I'm not going to be talking. I can, I just don't think it's very sensible. So what I'm going to do is I'm going to take a maybe a 10-minute break now, and when we come back, I want you to attempt the lab. Now the lab, I've just realised, was written for remote and working on your own machine. All I want to be sure of is you can access Quartus and you can access MultiSim, and you can do that on these machines. Right? So all you need to do for the first lab is basically take screenshots of being able to compile something out of something in Quartus and being able to do something, or just start up MultiSim. Really not. Okay. So let's take like I said, let's make it a 10-minute break. And we will be back and doing labs after that. I'm going to take a coffee break.
Professor, quick question.
Last year's
Okay, so like I said, I'll just give you a quick demo of the two things I want you to do for Lab 1, and then I'll get you to do that. So, first of all, I do not have MultiSim installed here, so I'm going to go to the app server, the Citrix server, and I'm just going to use the light version. I'm going to go to desktops and then the engineering, science and technology desktop, I believe is the one we need. And eventually that'll load up. The only thing Lab 1 does is tells me you have access to the two tools you need to do the rest of the labs. Okay, there we are. So this is just running in the browser rather than using the client. And I think I need to go with MultiSim. There we go, MultiSim 14.2. And that's all you've got to do. Right? I want you to take a screenshot of that. So that's that one. In fact, let's pull up the lab as it's written. I have put all the labs and all their due dates in here already. So let's have a look. So it does say download and install. If you want to do that on your own machine, that is okay. You don't have to. Now that we have access to these machines, you can do it in the lab and just fire it up in the lab. I would like you to think about using Git. Has anybody, well, some of you have already heard me go on about Git. Anybody not in Capstone heard about Git? One? Two? No? Okay, so when you're writing software, and I apologise for the repetition, when you're writing software, one of the things you want to do is you want to keep track of how the software changes. And the way you do that is a thing called source control. The source is the source code, the program. And the most popular program for doing source control at the moment is Git. And you've probably heard of GitHub and GitLab, maybe Bitbucket if you're into the Atlassian side of things. And I have put a couple of repositories up on GitHub for this course. And let's have a look at the main one. Now the main one is very big, so I wouldn't think about using that one. Use the second one, right? And the nice thing is, maybe, right, there's a picture of the board. There's an annotated picture of the board. There's some of the I/O of that big center chip, the big square chip. And there's some other bits and pieces. Right, so have a look at that. But the lab is basically, what I want you to do in the lab is, we haven't done anything about writing code yet, but I want you to compile some code in Quartus. So that test module will allow you to compile some code in Quartus, and that's all I want you to do. Right? Let me show you what Quartus looks like. Well, in fact, why don't we do this? Right, so there's the test module, and in Git there's a couple of ways, or at least in GitHub, which is this website, there's a couple of ways one way to get that information down onto my machine is to do a git clone. Right, and that'll go off and go grab everything from that repository. These machines all have Git installed. You can do it this way, provided everything's set up. I think everything should be set up. However, if you don't have Git installed, you can still do it by just using the, might be a bit hard to see because it's behind me. Where'd it go? There's a download zip option, right? If I select the download zip option, it'll download that into a zip file, and there it is there, and I can just extract everything from that zip file. That zip file will not be connected to the repository, right? And that's okay, maybe you don't need that. But that's now extracting everything from that zip file, and now I have an exact copy. The reason source control is really useful in software particularly is because oftentimes you want to make changes to implement the next thing or fix the next bug. And if you've ever heard that song, 99 bugs in the code, 99 bugs in the code, fix a bug, turn it around, 125 bugs in the code, right? That is what often happens. So with source control, you can then come back to a known good position in the code if you've made changes that break stuff. Okay, so I've downloaded that into that directory there, which is my this PC download CET466 test module master. Now I have already Quartus opened. One trick with Quartus is it uses file extension filtering. And if you just use open, and if you go to downloads, and there, right, it won't actually let you open the project because it won't show you the project because of it's looking for a design file rather than a project file. So be careful and select either project files or all files, and that'll give you the QPF file, which is the Quartus project file. Now, this particular project is not in VHDL, it's in Verilog. However, the aim is not for you to understand it, the aim for you is to just use it to compile. Right, so I should be able to hit the compile button. And that should all happen swimmingly there, maybe. You can see it does take a while, right? It's got up at 4%. Hopefully this will work out correctly. And what I want you to show in your screenshot is all of these things should be green, and there should be a check mark beside each of them. I'm wondering why it's taking so long. Oh, there it is. It's obviously hit something it didn't like. just about done with the analysis and synthesis. Now it started doing this and I don't know what the problem is. Hitting that button there should do everything, but it hasn't been doing everything. So sometimes you got to do all the next steps manually, and let me try and debug that. And I'll try and post something later. Okay, that's taking a while. And then the assembler. And then timing analysis. And then the net list. Okay, so you should have, by the time you've finished, you should have all of those green. And take a screenshot of it. I just thought I should show you. Let me see if this works. I hope it does. Now, where there it is there. There's the power. So these boards, you've got to connect 2 USB connections to them. I have a video up on YouTube to show you, but first of all is that USB connector, the old style one. That goes in there. And if you plug that in and then press the red button, you should get that little red LED. We won't be using these boards today, but I'll show you this again when we do. And then the other thing, turn it off before plugging the other one in. This is the programmer. And there's 2 options. There's JTAG and AS. JTAG, which is what we will use mostly. JTAG just loads up the VHDL program in RAM, right? So it'll run, but if you power it down and power it back up again, it'll go away. The AS input lets you program it into non-volatile memory, so that when you power it down and power it back up again, it reloads that program and it'll start again. Okay, so I'm going to power that on, and you'll see down the bottom here, maybe it's a bit hard to read, program device is the last thing in that list. Now I've already set this up. You may have to go into hardware setup and select the USB blaster on these machines. I don't know what state they're all in. And you should then just be able to go start, and you should get all green up here, and it's programmed the board. Okay, now the tricky bit. That program should, if I'm, no, wrong one, that one. There we go. So that program has put this, so it's a VGA card. None of you probably have worked with VGA cards, but it's the old, basically 8-color palette, right? And this particular one, it's set up so that I think it swaps it inverts the bits, right? And it can let you see the 8 colors there, which is kind of fun. The only problem with VGA is none of these monitors are VGA, they're all HDMI. Right? And this board doesn't have an HDMI output, which is a bit of a pain. But we can connect up here to show you VGA, and I have a monitor, an old monitor I can bring in if you want to do that way. Okay. Hopefully that comes up again. That's good. Okay. So the other one I wanted to show you is an example, a simpler example, which is a baseball counter, right? So in baseball, you have balls and strikes, and you want to be able to count up to, 3 full balls, and it's a walk, right? And up to 2 third strike, you're out. And you also, if they get a hit, you want to be able to reset the count, right? So that's what this one does, and I'm not going to compile it because of how long the other one took. It shouldn't have taken that long. I'm just going to use the code that's there already. And hopefully that flows. It does. Right, so there's the count, 0 and 0. And I should be able, right, there's the ball counter, and when it resets it flashes. There's the strike counter, when it resets it flashes a bit differently. You can do them both. When one of them resets, both of them reset. And then if you want to reset the whole thing, you just press that button to get it here. Right? So that is one of the labs I'm going to get you to do later on. Any questions? Okay. Grab a computer and fire up MultiSim and try and get that VGA project compiling under Quartus, please. So you probably won't need it for this lab, but I've just sent a link to in Blackboard out in a Blackboard announcement that will put you into or get you to take a number in a queue, right? And this is what I see to service that queue. When you take a number, it'll give you a number. It'll tell me here who the next person needing help is. Like I said, probably won't need it here, but I will use it so that I can come round to give individual help if needed. Yeah.
No, so in Blackboard, there's one I recommend. But that one didn't let me do it, so I downloaded it and I didn't Quartus network. Yeah. I don't know if we need to download it. That might be cool. I'm not sure. Just two screenshots is perfectly fine. Normally, I say
This one is just more trouble than it would start with.
Yeah. Yeah, everyone shows me the text there. That's perfectly okay.
Just load it up as screenshots.
Normally I prefer to read, but this time it's more trouble than it's good.
So how it will work because the program
No, you want to go yeah, sorry. Yeah, it's not as so you should be able to just go down and start walking.
Just wanted to submit a few screenshots and
That's it, yep. Nothing too taxing, I don't think.
I would say so.
that was really training actually.
Yeah, for the first day, a
Hmm?
little stressful.
Okay, once you've all done that, I'll bring you back and we'll talk about some actual content eventually. Gonna finish my coffee first. So if it wasn't clear, please just submit your lab as soon as you're done with it, and we'll be good.
Yeah, I think get the times mixed up too. I showed up at like 7:40 yesterday. For a seminar. I thought it was started
Okay. Yeah, you got a question? Sorry.
Okay, so what did you like? Yeah, so what it's asking is to download that one. Extract that. Because it needs to have code to actually run. And we have to put the code in. Right, so what you need to do is you need to open that program.
Oh yeah.
That should have you created the new project, and the new project didn't have the program, right? It's trying to compile a program, but can't compile the program. This is one I prepared earlier. Just a screenshot of that and a screenshot of that. Okay, so I want to talk a little bit more And if you check it out in OneNote, I have all of the VHDL slides I'm going to be using. Alright, so it's all there, even down to test benches, which is what I talked about in the project, and we'll be doing a lab on test benches before we get to the project. Before I go there though, can anybody tell me what that is? What the table is?
Any numbers?
Sorry?
Any numbers or all?
Yeah, they're binary numbers, 0 and 1.
Matter.
Well, yes, it's just the next lab, it's lab 2, so it's an adder. But what's this table called?
Truth table?
A truth table. Ah. So a truth table is, in this case, normally I'd expect a bit better split between the inputs and the outputs, right? But a truth table will usually enumerate all the possible binary combinations of inputs and outputs. Here we've got 2 inputs, so that means we have 2 to the 2 possible combinations of inputs. So 2 squared, 4. And what's showing here is the carry and the sum. Right? So this is, I think it's a half adder, so 0 plus 0 has 0 carry and 0 sum. 1 plus 0 has 0 carry and 1 sum. 0 plus 1 has 0 carry and 1 sum. And 1 plus 1 just has a carry. Right, that's all it's doing. The next lab is about implementing that in MultiSim to start. And we'll talk about how that might work. So does anybody remember, given these inputs and say, let's say the carry output, does anybody remember how to figure out what that function is? Let me go to my app and I'll call on somebody to tell me how to do this. I'll just reset it so we can start from scratch. Okay, so again we'll so Fahim, given you've got a truth table, can you explain how you might go about finding out the Boolean expression, or another way of doing the circuit, the logic circuit? Because those 3 things, the truth table, the Boolean expression, and the logic circuit, are the same thing, really. They're representing the same idea. Any ideas how you'd go about taking that truth table and going to either a logic circuit or a Boolean expression?
Just when you have added numbers and give you the result like true or false, on and off.
Right, so here we have false, false gives false, true, false gives false, false, true gives false, and true, true gives true. Right? I'm just talking about C, I'll talk about S later. How do we, any idea how we might go about getting that, like I said, either the circle or the Boolean expression?
We added up the numbers.
Yeah? What do you mean by adding up the numbers?
True and false. It's false.
Okay.
That's what it is.
Okay, let's see if somebody else. David.
So again, 0 and 0 equals 0, that's kind of like the same thing. And so, but it's or, I don't think it's an or, because if it was an or, it would be 1, 0 would be 1.
Okay.
I think that's, it's probably an and, or, is it and or exclusive and?
It is an and.
And, yeah.
Right. So the nice thing I'm hearing you say is or and, right? So let's just go here and let me see if I can do some drawing. Right, so we're on lecture 1 and let's go back here and let's just paste that in here. Maybe? Doesn't seem to want to do it. Let's save the image. So this is half-added truth table, and let's see if we can just insert the image from a file. And there it is there. Right, so there's where did we pick it? There it is. So there's lots of ways to represent logic, and I talked about the 3 before. There's this way, a truth table, there's Boolean algebra, and there's a circuit, right? And they all 3 represent the same idea, right? So there's this is the truth table. There's also Boolean algebra. Right? And there's a circuit. A logic circuit, really. And the things we want to be able to do are to represent the relationship between inputs and outputs, right? So here, wrong way, here we go. So here, we had heard an essay or and, right? They're the two of the basic operations. And Bright, can you tell me what another basic operation, logic operation is? We've got and, so A and B. We've got or, A or B. Is there another logic operation we could add to that list?
No.
NAND? Yeah.
right? So we could have a NAND, which is not AND. I suppose the simplest one would be the NOT operation, right? If you are on Discord, you might have seen this joke, right? This isn't a joke. This isn't a joke. There's the AND gate, the OR gate, the NOT gate, the NOR gate, the XOR or exclusive OR gate. There's the NAND gate that Bright talked about. It's the same as the AND gate, except it's got a bubble on the output, so it's negating whatever's behind it. So that's not AND. And then it starts getting silly, right? A NORX gate, a GAND 8, a ZAND GUNT, a NORGZUNT. These are all silly, right? So the aim, you don't want to, I don't mind being a little silly, but for here if we're actually going to design circuits, we've got to use the right things. So there's others. I think the list up there, we had a NOR, we had a XOR. That'll do for now, right? And we can represent all of these things in these three ways, right? The Boolean algebra, right, if we had A or B, that's a way to write it, but the way I'd more usually write A or B is like that, right, using the plus symbol. Don't get confused. Don't confuse the plus symbol with an AND. It's not an AND. It's an OR. Right? So A or B. In Boolean algebra, the AND, I probably should have given myself more room. So let's just erase the circuit for now. Right, we could have said A and B. And one way to write that is as a dot, or sometimes you just write it out as AB. Right? You don't bother with the dot. Not. There's a couple of ways to write that. Right? One way is with a bar. The other way is with a prime symbol. Right? That's a not. And each of these has its own specific truth table. And Anas was right in saying that C is just equal to A and B, which is equal to AB or A dot B. Okay, I should scroll that up a bit maybe. Right, so you can read it. And then the logic circuit version, I keep wanting to write on the... What was that? The logic circuit version has A, B going into the AND gate, and that's an AND gate, not an OR gate. Right? So there's our logic circuit. And all three of these are saying exactly the same thing. It's telling us the relationship between the inputs and the outputs. Oops. No, I didn't want to do that. So all the second lab is asking you to do is to simulate a half adder in MultiSim. And then I want you to show that the half adder implements that truth table by exercising the circuit. Right? This is working towards that whole idea of testing when you get to VHDL. Okay. I'm going to give you time next week to do lab 2. If you want to play with it beforehand, feel free to get it done before then. That's okay. But we'll have, the aim is to have time next week to let you do that. Just again to check. Right, that lab 2 is not due until 2 weeks from today. Okay? Okay, let's go back. And from here and here, I do want to talk a little bit about this one. Okay, so VHDL. I'm going to chop and change between low-level stuff and this higher-level stuff. One of the ideas in teaching is called interleaving, right? And the idea is that people tend to retain information better if you don't just talk for 4 hours about logic circuits, or rather Boolean algebra. If you talk a little bit about Boolean algebra and then talk about VHDL and then talk a little bit more about logic circuits, etc. Right? So I intend to not arbitrarily change, but I intend to give you some high-level stuff and low-level stuff. Okay, so VHDL. It should actually be VHSICHDL, right? But that's a bit too long of an acronym, so it's VHDL. Very high-speed integrated circuit hardware description language. Its original intent was not to actually be able to synthesize functionality. Its original intent was just for documentation. However, now we can synthesize using it. And because this came out of DoD, the Defense Department, they were very keen on verification. Right? They wanted to be able to check all the boxes to say, yes, this thing does what it says it does. And that's where VHDL came from. VHDL is an IEEE standard. IEEE is the Institute for Electrical and Electronics Engineers. And I am reasonably active, or at least I have been until recently, in the local chapter, the Connecticut section. There is an IEEE club here on campus for students. Last time I checked, they were playing with a thing called Ducky Town, which is a robotics simulation environment and deployment environment, which is kind of fun. Does anybody know what strong data typing means? Any thoughts? So if you've programmed in Python, right, it's possible to declare types, float, integer, more complex types, but it's not necessary. Some languages require strong types. Strong types means I cannot assign a variable of one type to another type. C, you can do a thing called typecasting, which lets you force an integer into a float or force a float into an integer. Some languages don't let you do that at all. So you've got to figure out something. VHDL is a strongly typed language. It's hard, though not impossible, to convert from one to the other. And the reason is safety. Right? When you want to try and do something with the wrong type, you want to make it hard for a programmer to do that. Because otherwise they will make a mistake, I can guarantee it. I've done it lots of times. Right, so this is talking about multi-value logic, right? And as it says, where you can have more values other than 0 and 1. Have any of you ever worked with card readers and swipes, access control systems? Right, we've got one here. Right, I had to use this on the door to get in. And I don't know if you've ever seen the LED on those doors. But if I just present my card to the door, the LED is sort of in an intermediate state. I think it's actually flashing between red and green, but it appears to be a yellowy colour. Right? And what is happening there is it's sort of displaying multi-valued logic. If I present my card and then type in the wrong pin, the LED will glow red. If I present my card and type in the right pin, the correct one, it'll glow green and open the door for me. Right, so that's one use of multi-valued logic. Another thing that's interesting from a multi-valued logic perspective is oftentimes you want to be able to receive data and send data on the same inputs. If you've ever worked with microprocessors, things like a Raspberry Pi or an Arduino, those devices have things called GPIOs, general purpose input-output pins. Right? The way they do that is they have something like this. Anybody know what that triangle is called? I'm just waiting for the Eric, where's Eric? There he is. Do you know what that triangle is called? No. Let's try somebody else. Muhammad, do you know what that triangle is called?
In words?
Sorry?
In words?
Well, if it were an inverter, it'd have a little bubble on the output. Close. Emily, any ideas? Okay. So that device, I keep wanting to write on the mouse pad for some reason. Right, so if you see something like that, that's a NOT gate or an inverter. This one doesn't have that bubble. The bubble is the thing that's doing the inversion or the NOTing. If you see something like this, this is just called a buffer. Okay? And the truth table for a buffer is just that. So what's happening here is it's like a switch, right? Here, if this is a TX and transmit is going that way, it's going to turn this one off and turn this one on and turn this one off so we can get our signal out that way. If it's the RX mode, then this one is turned off and this one is turned on so we can receive something. That device is called a transceiver. And it lets us connect multiple inputs and outputs onto the same wire, onto the same bus. We just have to make sure we only turn one output on that bus on at any one time, but it's possible to read multiple things at once. The reason why you might want a buffer is because even though we think about these things as Boolean algebra, they're actually electronics, right? And electronics require current to work. And one of the problems with logic is a thing called fan out. Right? If you have an output and you connect that to lots and lots of inputs, it's possible that that output doesn't have the current capability to drive all of those outputs. So sometimes you need to put not just a transceiver, just the buffer. You need to put a buffer in the way to allow that higher level of fan out to get more connectivity happening. So that's just right. Effectively, that's what it looks like. You've got a FET or something like that up here, right? That turns the input high impedance if it's not being used, or turns the output high impedance if it's not being used. VHDL is about designing logic, and as we've just talked about, logic is 0 and 1. However, because of this issue with multi-value logic, VHDL variables can have values other than 0 and 1. They can have 0 and 1. That's a given. If they're in this high impedance state, they can have a value of Z. Right? And that means it's indeterminate as far as a 0 or 1 is concerned. There's other values that a VHDL variable can take. It can take the value H. And H means it's probably a 1, but we're not quite sure. It can have a value of L. It's probably a 0, but we're not quite sure. And there's a few others. If you have a look at the, why don't we try and see it now? If you have a look at I think it's on the fall 2020 final. I think. There we go. Right, so one of the questions is, what do these things mean? And they're all the possible values that VHDL Boolean values can take on. Stdit logic, that's called. U, X, 0, 1, Z, W, L, H, and minus. I'm not going to read the slides. You can read them better than I can. I will talk to them briefly. We want to be able to make up other types. We want to be able to make up bit strings or arrays of bits. We want to be able to deal with floating point numbers. We want to be able to deal with fixed point numbers. We want to be able to deal with arrays of those things. So VHDL has that capability. Right, just like just about any programming language. Alright, so there's one of the key things you'll see in just about every VHDL program I talk about. It'll include the IEEE library. And the IEEE library has a lot of this stuff in it. Particularly the stdit logic type, which is very useful. And this diagram, if I can get it on the screen, there we go, is sort of related to my meme on the first slide of my presentation, right? We've got specifications, algorithms,
registers, state transition maps, Boolean algebra, and then we start getting into individual electronic devices, and then down onto the silicon, onto the physics. And the things we can do in VHDL is basically everything above the circuit. We can do individual AND or OR gates. It's a NOR gate or a NOT gate. But we can build up complete systems as well, which is kind of nice. There's two words you'll hear me use for different ways of representing logic. One of them is behavior, and the other one is structure. And it effectively, it gets a bit more complicated when it's more complex than this, but it's effectively the Boolean algebra way of showing it and the logic circuit way of showing it. They're the two things. You may recall when I showed you that question from previous exam that there was a thing called an entity. And when you're designing logic, one of the first things you've got to think about are what are the inputs and what are the outputs. And that's where entities come in. It defines the boundary around the thing you're trying to design. The other part is what happens inside the box, right? And that's in VHDL, that's the architecture. All right, so we can do that. The other thing in VHDL is we might want to make something, a component, we might want to test it, and then we might want to use it in a bigger system. So here we've got several adders, and we want to use it in a bigger system. So we can connect those individual components into the bigger system. Within each box, there are things called internal signals, and the things connecting the boxes are the external signals. Okay, here we get to. And I've already talked to this, right? The entity is the interface description. The architecture is how the inputs relate to the outputs. And anytime you see the extension we use for VHDL files is .vhd. If you ever see a .v file, like in that VGA example that we compiled earlier, that is a Verilog file, and I'm not going to touch Verilog in this course. So VHD. I'm not going to go into the detail work until we talk about, well, we actually get to do some of that stuff. And I think I'm going to leave that there. Okay. That was a reasonably high level introduction to VHDL. We're not going to touch VHDL until probably lab 3, I think it is. So we're still a way away from that. Any questions so far? All good? Okay. So it's about 11:30. I'm going to take another 10-minute break. And when we come back, I want to go back to that lower level stuff and talk about other sorts of devices that we need to think about, other than just AND gates and OR gates and that sort of thing. And also a little bit carry on that conversation about how to connect truth tables with logic circuits with Boolean algebra. Okay? So let's 10-minute break. Okay, let's go back to it. So I just gone through and graded all of the submitted lab ones, and thank you for that. As I said, it was perfectly okay to just submit two JPEGs. Normally, I don't like that. I prefer one of two formats, either Word or PDF. Doesn't matter for Lab 1. From now on, though, the labs are a bit more complicated, and I'm going to expect you to write up a proper lab report. And I've just uploaded into the OneNote this thing I wrote back in 2019 that goes through what I look for in a report. This is over and above what I'm looking for in the lab reports for this class, but it'll give you an idea about what you should put into it, right? And the format of this write-up is what I'm looking for, right? This is way more wordy than I expect most of your lab reports will be, but I do expect a summary, an abstract. I do expect a brief introduction. And the reason you put an introduction is, why should I want to keep reading, right? You want to tell the reader what to expect. There should be a problem statement. What am I trying to show? What am I trying to solve? There should be something about how you're doing the lab or the procedure or whatever it is. There should be enough information that another student, should be able to reproduce the work. Yeah, that's the aim. And then there should be there should be results. Sometimes this will be graphs, sometimes we do need to do timing diagrams, which is sort of like graphs here. So that may be, so make sure that you've got axes labelled and it's clear, and whether it's logarithmic or what have you. I don't know what I'm doing. Make sure that the axes are labelled, make sure you've got a caption on the figure. I don't think I put it in here. When I used to manually grade lab reports, if I saw a graph that had no idea what the X and Y units on the axes were supposed to be being displayed. On the X-axis, I would write furlongs per fortnight, right, which is a measure of speed in some arcane value. And then on the Y-axis, I would say litres of blue cheese, right? Because it could just as well have been litres of blue cheese if it's not labelled, right? So these days that's probably a little bit too, I don't know whether the word's passive-aggressive or whatever. I thought it was funny at the time, but maybe some people mightn't like that. So I will just say, please label your axes. There should be a discussion, and then there should be a conclusion. If you read through the list of labs, you will see some of them follow on from each other, right? So in the conclusion of one that you know is going to go to the next one, you should probably say, I'm going to use the result of this in that lab because, right? So try and at least have a little bit of a look ahead. Now, as you can probably tell from my accent, I did not grow up in this country. So my
slant on the language I'm speaking at the moment is from the British side of the world, Australia in particular in my case, right? So I don't speak American English. Well, I do at this stage, mostly. But I still fall into some of the Australian idioms or sometimes the Irish idioms. I lived in Ireland for about 5 years. My wife is Irish. So I am not a big stickler for spelling, grammar and formatting, except when I can't understand what you're saying, right? And if I can't understand what you're saying, then I need to correct, or at least I need you to correct that. Right, so I will use it, but sparingly and with a view to understanding more than anything else. We probably won't need to reference much in this, but if you do, make sure you have a reference list and you reference in an appropriate way. My preferred reference citation style is the IEEE style. There are other equally valid styles. There's APA, I think, is the physics style. There is the Chicago Manual of Style version. There's all sorts of different perfectly legitimate ways of citing. I don't care which one you use, except I would prefer the IEEE, but it's up to you and who you're reporting to. Okay, so all of that is available in OneNote. Any questions about reports? I just wanted to check to see right, I normally put a rubric in here. Okay, this one is specific for this one. So these are the things I'm looking for. I think I have a more general rubric. Let me see if I can find one of the later ones. Right, so this is a more general, right, it's looking for those specific parts of the that I identified in that PDF. Okay, so some of the later ones. Okay. Okay, so let's talk more about logic. Here we've got logic functions, but there's a whole other area that we need to talk about in, well, that you would have covered in 363 and that we need to talk about again here. Any idea what else we need to talk about? Any topics come to mind? Let me pull my trusty app up and see if I can. Michael, you couldn't tell me?
Matthew. Matt.
I'm not sure.
So, remember what this was doing. This is a baseball score counter, right? Ball strike counter. The only inputs that I can see on this are those switches. But none of the switches are being touched now, but it doesn't have 0 and 0 there. What I'm looking for is, this is one aspect of logic, right? Inputs lead directly to outputs. The trouble is, you also need to be able to do what's called sequential logic. Right? You need to be able to remember what's happened and do something different the next time, so that we can count balls and strikes, for example. Right? So there needs to be some sort of memory in there. That's usually what is happening with sequential logic. And let me go ask another question. Michael, what's the thing you would use for memory in digital design?
What's the thing you would use for
What's the
memory?
device you would use for memory? The lowest level memory device.
It's a good question.
Do you have a good answer?
I don't know what it is.
That's okay. Let me pick on someone else. Michael. Sorry? So the question is, what device would I use in, you'd probably use them in 363 to store memory information. But the lowest level, and the lowest level is 1 bit. Sorry? Sorry, I can't hear you. That might be a little too low level. Let's think up a little bit. And let's try David, any thoughts? No, that's okay. So what I'm looking for is a flip-flop. Right? A flip-flop is effectively a 1-bit memory. Huh? And so when we design sequential circuits, at least when we put them into MultiSim, we have to use some sort of a flip-flop device to store that information. Now let's have a look. It was on the midterm. No, it wasn't on the midterm. No, it wasn't on the midterm. Oh,
because it was in a completely other course. Well, so. So when we design sequential logic, we need to have an idea about how things change, right? And the usual way to indicate or to do the design on sequential logic is to draw, that's really badly drawn, is to draw something like a state diagram. Right? And the state diagram tells you how you move from one state to the next state. And normally each of these transitions will have a particular logic function that says when this logic function is true and you're in this state, this transition happens. Inside each of these, there's usually two things. There's a label which says state A, state 1, whatever the naming convention you're using for your states is. And there's an indication of what output happens at that state. Right? So there's usually two things inside each of these circles. Once you've got the state diagram, then you can think about how many states do I have, right? In this case, I've got 1, 2, 3 states. Then you can think about how many flip-flops do I need to represent those states. Any idea how many flip-flops I need to represent those 3 states? 1, 2, 3. 3. I reckon we need 2, right? Because each flip-flop can be in either 0 or 1. So if they've got n flip-flops, we can represent a number 2 to the n. So if we've got 3 states, we can't just use 1 flip-flop because we can only represent 2 states, on or off. But if we've got 2 flip-flops, we can represent a total of 4 states. Okay. Just remembered something. Does anybody remember when you've got a flip-flop, what thing describes how the flip-flop works? There's a particular name. It's sort of like a truth table, but it's not a truth table. Can you go pick on somebody again? Venn diagram. The Venn diagram's the 2 circles and 3 circles, right? Fahim, any idea what is used to describe how a flip-flop works? How about right? Any ideas? No. Okay. So the word or the thing I would use to describe a flip-flop operation is called an excitation table. And basically an excitation table tells you for the flip-flop, given the present state and the inputs, what's the next state for the flip-flop? Right? So does the flip-flop change state on the output? Does the flip-flop stay in the same state? Can we determine what state the flip-flop is in? Some simpler flip-flops, you can get them into an indeterminate state. If you're designing a sequential circuit, you've got the state transition diagram. From that state transition diagram, you can generate a present state, next state table. That present state, next state table, you can then use to say, okay, here are my inputs, the present state, the values of the flip-flops on our present state. This is the input, and this is where I need to end up in my output. That's the next state, that's the outputs. You can use, well, you choose what sort of flip-flop you're going to use. Could be a D flip-flop, could be a T flip-flop, could be a JK flip-flop, could be an RS flip-flop. I hope all of those have some familiarity, but we'll go through them. And then you can design the logic that is applied to each flip-flop from the present state, next state table. Right, so you get the present state, next state table. You decide which flip-flop to use. And then what you can do is you can write either the logic or the truth tables to force the flip-flops to make those transitions. And let me just scroll that up a bit. Okay, so I'm talking at a pretty high level. I need to show you an example. I will see about showing you an example shortly, but first I want to go back and look at flip-flops. Right, so and let's just go here and look for flip-flops. And they're not the sort of flip-flops we want, are they? Okay, so let's go to Wikipedia of all places. Right, so let's just see if I can make that bigger. There you go, that'll do. Right, so we've got SR, set, reset, flip-flops. They're really simple and probably not what we want. There's a JK latch, which is also getting a bit more complicated, but also possibly not what we want. We want to probably need some gating. Probably a first real flip-flop we might want to use is a D flip-flop. Let's have a look at that. Alright, so for a start, there's our D flip-flop. So, Michael, can you tell me what that one is? What that input there is? The one with the triangle. Sorry, I can't. Brown? No, that would not work. And us, any thoughts?
Kind of looks like a buffer.
It does look a little bit like a buffer sign. It's actually, I hadn't noticed that, but I can understand why you're saying that. It's not a buffer. Emily? No? One more. Matthew, Matt.
I'm not sure.
Not sure? That's okay. So, I'm just trying to think about the right way to say this. When we have AND gates, right, we have A and B. When you change the input on A and B, the output, if it changes immediately. Right? There's nothing in the way. That mode of operation is often called asynchronous. And asynchronous behavior is okay at a simple level, but it can get very complicated very quickly. So what most digital devices do, computers, monitors, they work in what's called a synchronous mode. That synchronous mode is, funnily enough, synchronized to something, and that something is usually a clock, right? It's a thing that is changing exactly the same way a certain number of times a second, right? I don't know what these machines have. Let me do it on mine so we can see it. Right, so we go to this PC, and this is a really old computer, but this one is running at 2.3 gigahertz. Right? That means that the clock is changing 2.3, what's the word, billion, with a B, times a second. 2.3 by 10 to the 9 times a second. And that's what this is. this is a clock input. Anytime you see that buffer sign, I didn't realise the confusion. So that is an indication that that's where the clock input goes. Okay. Let's pick on someone else. Eric, what's the S? No? Don't remember that? Let's try Michael.
Or maybe the set that we were talking about before.
Exactly. That is the set, and this one is the reset. Exactly. So flip-flops let you change the output. Here's the non-inverting output. Here's the inverting output, right? This one, if this one is a 1, this one should be a 0. This is Q bar. And here's our data input. Flip-flops allow you to change the output based on the data, but sometimes you want to force the output, and that's what the set and the reset inputs are for. Okay. Let's just have a quick look at so I hope you can read that. Let me just see if I can make it a little bigger. Where did I go to? Where did it get to? Here we go, D flip-flop. Right, so it's otherwise known as a data or delay flip-flop, and it captures the value of the D input at a definite portion of the clock cycle. Right, remember the clock cycle is probably doing this, and my drawing is not as good as it could be, but the aim is that each of these high and lows are the same duration, and it just keeps doing it. And the idea is that, let's just get a different color, let's go with green. The idea is that at some portion of the clock cycle, possibly in the high region, that is when something happens, that that D input is read and propagated out to the Q output. Let's just go back and see what's happening with the right, so, and in fact what's happening, it's not even, I was wrong, okay? It's not happening at a flat path, it's happening at the rising edge. Right, so what, oops, wrong one, that one. So it's actually happening, this is the rising edge. Right, so it's going to happen at each of these. This one here, that's the falling edge. It's not happening there. It's happening on the rise. This particular one, it's happening on the rising edge. right? And so anywhere else, it's got an X. And whenever you see an X in logic, that means I don't care. That can be any value you want. So if there's a non-rising edge, so it's flat, it keeps the previous value. Right? X denotes a don't care. And here's what happens with the set and reset values, right? If set is 0 and reset is 1, then we reset. If set is 1 and reset is 0, then we set. So reset is setting Q to 0, set is setting Q to 1. If both inputs are 1, we have this ill-defined condition where both the Q and Q bar outputs are 1. Let's just see if I can...
Professor?
Yep.
Can you give us an example when both the set and reset will be 1?
No. Well, I could, but it's usually, well, it is an undefined moment, right? You usually don't want Q and Q bar to have the same value. It's just the way this is implemented has that unfortunate consequence. Normally, what you would want in this condition is you would want Q to be here and Q bar to be here, right? So it would have the same operation as if both S and R were 0. You usually don't want that condition to happen. Okay. It's usually not a good idea. Okay. Let me just see. Yeah. Right, so this, let me just open that up in a separate tab. Right, so here we've got some examples of excitation tables. And I said these are the things you would use if you're designing a sequential machine. The D flip-flop is here, right? So if we want to transition from 0 to 0, the D input has to be 0. If we want to transition from 0 to 1, the D input, it's just a delay, right? So it's just taking the input and copying it to the output. If we want to transition from 1 to 0, D is 0. If we want to transition from 1 to 1, D is 1. We can take that information and make the decision we're using a D flip-flop, and we can then go about designing the logic on our state, from our state transition table, or our present state, next state table, to figure out how to drive D on each of the flip-flops we're going to use. Okay. Just trying to think what the next thing to talk about is. Okay. So we have our, I'm going to go back to that example where we have our carry bit, right? We have our A and B inputs, 0, 0, 0, 1, 1, 0, 1, 1, and the carry bit was like that. Let's say we had some other value D. I could write D as a Boolean expression as, and let me think about this. This is going to be Z1 ANDed with A bar B bar, or Z2 ANDed with A bar B, or Z3 ANDed with A B bar, or Z4 ANDed with A B. Let's just move that up so you can see it a bit better. That way of writing, moving from the truth table to the Boolean algebra expression, is called the sum of products approach. Okay? So this is called the sum of products, or SOP approach. And that's the, if you like, just the mechanical way of moving from a truth table to a Boolean algebra expression. Now we can try applying that to C, right? So C has Z1 as 0, Z2 is 0, Z3 is 0. So these first three terms don't count at all. So the only term that counts is C equals 1 and AB, which is just the same as AB. Okay. So for C, I set Z1 to 0, I set Z2 to 0, I set Z3 to 0, and I set Z4 to 1. That's a mechanical way of moving from one to the other. That same thing, that same approach works regardless of how many inputs there are. Right? If I have A, B, C, D inputs and an output X, oops. This is going to take me a while to write up, but I'm just going to count up in binary. So 1, 0, 0, 0, 1, 0, 1. Zero, 1, 1, 0. 0, 1, 1, 1, and then I do the whole thing again with the high bit 1. I think I got everything. Let's just check. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Right? I got 16. And I'm not going to write it out, but if I have Z1, Z2, Z3 all the way up to Z16, I can then just write Z1 times A bar, B bar, C bar, D bar, etc. That gets very complicated very quickly. So there's two things. One of them is to have maybe a more compact way of writing a larger truth table. And the other way is we often want to simplify the logic expression. Right? So there's a thing called a Carnot map. Anybody remember Carnot maps? Remember the name at all? Yeah? Right, so a Carnot map is a way to redraw the truth table in 2 dimensions. Right, so what I can do is I can have A and B on one axis and C and D on the other axis. Right, and let me get this right. Okay, and let's just take a few examples. Z1, Z2. So Z1 is AB00 and CD00. So we put Z1 in there. Z2 is also AB00 and CD01. So we put Z2 there. Then this one is actually going to be Z4 and that's Z3. Okay, so I can take the entry here and put it here. I can take the entry here and I can put it here. And for a start, like I said, that gives us a more compact way to represent more complicated truth claims. The other thing it does, though, is it allows us to simplify Boolean algebra expressions. Right? So let's just see if I can draw another one. So if I have A, B, C, D, I probably should have drawn up some of these beforehand. So that's so let's just put in some random numbers. 1, 1, 0, 1, 1, 1, 0, 1, 0. And let's make all the others 0. Okay, so now I have a truth table with 4 inputs and 1 output. And I've represented it in a Carnot map. Alright, so let me just write the word Carnot map up there somewhere. Okay. What I can do is I can use this now to simplify the Boolean expression. Right? If I just wrote down each of these ones, I'd get a sum of product expression as A bar, B bar, C bar, D bar. That's that one there. Or A bar, B bar, C bar, D. Or A bar, B bar, C, D bar. That's that one. Or at A bar, B, C, D. That's that one there. This one here is or A, B, C, D. That's that one. And then the last one is A, B bar, C, D bar. That's if I just write down the sum of product expression directly. Right? But I can simplify using the Carnot map by grouping together 2, 4, 8, or 16 ones together. In this particular example, I can only do it in groups of 2. And I can obviously group those 2 together. And I can group those 2 together. Now, there's a tricky thing with Carnot maps, and the tricky thing is that this edge here wraps to this edge here, and this edge here wraps to that edge there. So what that means is this one here is beside this one, and this one here is also beside this one. Okay? So you can think about this Carnot map as being on a donut, right? Because this one wraps to here, which gives me a cylinder, but then this end wraps to that end, so I bend the cylinder round to be a donut. So I can actually group that one together with that one. Once I've covered a 1, I don't need to cover it again. So even though I could group that one with that one, I don't need to from a simplification viewpoint. It just makes it more complicated. So once I've covered all the 1s, I'm good. So what that tells me is it tells me because I've grouped those two in the top left here, it tells me that the value of D doesn't matter. Right? Like D can be 0 or D can be 1. So I can ignore it. So for for this one, that term is just A bar, B bar, C bar. And then this term, which one doesn't matter? Well, A doesn't matter because A can be 0 or 1. B has to be 1, C has to be 1, and D has to be 1. So that's B, C, D. And then these two, which one doesn't matter? Well, A doesn't matter again because A can be 0 up here and 1 down here. B is B bar, so this one is B bar, C, D bar. And I hope you can see, let's put that in full screen. I hope you can see that the red expression, even though it's a sum of product expression, the red expression is much simpler than this one. And I haven't had to do Boolean algebra to get there. I could do some Boolean algebra here to get the same answer. But I don't have to. Right? It gives me a way of getting there graphically, which some people don't like that, but some people find it easier to visualize how to simplify it. Okay. So I'm giving myself a few things to do for next week. I think I'm going to leave it there for this week. Does anybody have any questions, concerns? You should have done Lab 1. If you haven't done Lab 1, do Lab 1. It's not that hard. Please, if you haven't registered with the textbook, please register with that as soon as you can. I will either reopen or make a new initial participation activity. The people who've already done the participation activity, I'll give you a bonus because you did it early. I didn't expect I actually didn't expect anybody to have done it by this
I will release, there is also now a challenge activity available again in the textbook, so you'll have to get that. I will release probably later this evening the participation activity to prepare you for next week's lecture. Have a read through Lab 2. We will be doing that in the lab in this session next week. I'll see, I might, depending on how much I want to get across, I may also, I was going to say we might do Lab 3, but I don't think we'll do